welcome to the AI with Arun Show. We often talk about the AI arms race in terms of code, algorithms, and computing power. But in this episode, I want to take you beneath the silicon surface to the real battleground, rare earth minerals. This is the material foundation of technological supremacy, and its control is fueling what many are calling the next tech Cold War. The strategic competition between nations over these obscure metals is defining the future of technology, energy security, and global stability. Rare earth minerals, the critical battleground. Now, if you look around yourself, every modern artifact, your smartphone, your electric vehicles, even the powerful data center servers training advanced AI models relies on an invisible thread woven from rare earth elements. These minerals are the indispensable materials enabling our high technology civilization and driving the green energy transition itself. The challenge is that the global systems built to extract, to process, and distribute these materials is characterized by a profound geopolitical imbalance and systemic fragility. The race for AI dominance is intensifying, and without a secure, stable supply of these essential building blocks, the rapid advancement of nearly all critical technologies, from autonomous systems to defense hardware, is fundamentally at risk. We have, in effect, built our future on geological and political fault lines, and we must understand this dependency to manage the strategic future. So, what exactly are rare earth elements? They are a group of 17 metallic elements, including the lanthanides, the yttrium, and scandium. They are indispensable due to their unique magnetic and conductive properties. Now, here is a key fact. The term rare earth is actually a misnomer. These elements are relatively abundant in the Earth's crust. Their rarity lies in two areas. First, finding them in concentrations that are economically viable to mine. And second, the highly specialized, chemically intensive, and energy-hungry process required to separate them and refine them into high purity materials modern technology requires. They are typically categorized as light rare earths like neodymium, crucial for permanent magnets in EVs and wind turbines, and heavy rare earths like dysprosium and terbium, which are vital for military grade magnets that must operate in high temperature environments. So remember those two terms, light REEs and heavy REEs. Rare earths are not simply an add-on. So let's be very clear about that. They are used in every layer of the AI stack. So let's break down where this material dependency hits hardest. First, consider high performance computing. Data centers, the backbone of AI development, rely on powerful magnets made from neodymium and dysprosium to achieve faster processing speeds and greater energy efficiency. Dysprosium is specifically used to enable these magnets to function at the elevated temperatures found inside data centers. Second, the rise of physical AI. As we shift towards robotics and driverless vehicles, mineral demands are soaring. The electric motors in EVs and humanoid robots depend on these rare earth magnets. EV motors are, in fact, one of the fastest growing sources of demand. A critical mineral shortage will absolutely hamper any country's progress in this field. The third is semiconductor industry. Even the microchips themselves require rare earth elements. Cerium oxide is essential for wafer polishing, which is a critical step called chemical mechanical planarization, or CMP, in the chip fabrication process. Now we arrive at the central concentration risk. For decades, China has executed a deliberate strategy to dominate the entire rare earth value chain, extending from the mine to the finished. The statistics are astonishing. China commands approximately 80% of the global rare earth processing and refining operations. Crucially, China's refining capacity exceeds its own mining production by 30 to 40%. This means that even if a rare earth ore is mined in the US or Australia, it often has to be shipped to China for the complex refining steps that transform raw ore into usable materials. This is truly a choke point. China also controls an overwhelming 90% of permanent magnet production capabilities, which are essential for electric vehicles and wind turbines. Furthermore, Beijing controls 98% of the world's supply of gallium. The total dominance is a result of 4 decades of deliberate industrial policy, subsidies, and a strategic tolerance for environmental costs that Western competitors were unwilling to bear. China's dominance is not just a market advantage, it's a profound geopolitical lever. Beijing has demonstrated a clear willingness to weaponize rare earth supply as an instrument of statecraft. The most famous historical example occurred in the year 2010 when China temporarily restricted rare earth exports to Japan during a diplomatic dispute. This action sent immediate shockwaves, highlighting the deep vulnerability of technology dependent industries globally. Most recently, the escalation continues. In December of 2024, China banned exports of gallium, germanium, and antimony to the US. Then in April 2025, it announced additional export controls on 7 medium and heavy rare earth elements. This vulnerability is a serious threat to US national security. The considered military readiness for the US. Export controls may delay the government or the development of advanced generation aircraft, ships, and warheads, risking US strategic deterrence. The dependency is absolute. A single F 35 fighter jet requires approximately 920 pounds of rare earth materials for its advanced sensor and targeting systems. Now, this gives you an idea of the kind of dependency that we are talking about and the scale that we are talking about. Now, if we are going to fix this problem, we must understand its most critical weakness, which is the midstream processing gap. The raw material by itself is not the issue. The lack of refining expertise is the issue. The refining process involving separation, metallization, and magnet manufacturing is highly complex, technically challenging, and capital intensive. China's dominance in this midstream area is the key vulnerability. The capacity disparity is startling. China holds an 85% global share in rare earth separation, while Europe controls a mere 3%. Think about it, China 85% and Europe 3%. The US also lacks domestic processing capabilities, meaning ore from its only active mine, which is Mountain Pass, has historically been sent to China for refining. Replicating this ecosystem is a huge undertaking. Experts in the industry estimate that achieving just 50% self sufficiency in Europe, not 100%, but just 50%, this would require an investment of 15 to 20 billion euros and take 5 to 7 years of dedicated, complex development time, often struggling to reach cost competitiveness with China's subsidized model. Let that sink in. So, faced with this bottleneck, Western countries are fighting back by investing heavily in domestic resource development and leveraging advanced technology. The US Department of Defense, Department of War, has allocated over $439 million since 2020 to establish domestic rare earth supply chains. This aims to reduce reliance on imports for critical elements the nation currently sources entirely abroad. The exciting part is how AI is accelerating this hunt. The DOE supported National Energy Technology Lab has developed an AI powered prospectivity forecasting model called GAIA. Instead of relying on traditional decade long geological surveys, this model rapidly analyzes vast data sets to predict where critical minerals might be hiding in unconventional sources such as coal and clay. This led to stunning success. The discovery of the largest known source of magnetic rare earth element is the United States at the Brook mine in Wyoming, derived from unconventional sources. This innovation proves that with the right tools, we can accelerate resource development that historically took decades, securing our future supply chain under our feet. Because no single nation can overcome China's structural advantages alone, alliances are essential. The strategy is to weave a network of politically aligned, resource rich partners. Key partners include Australia, Canada, and Brazil, which hold 23% of the world's rare earth element reserves. The US and Canada, for instance, established a joint action plan to build North American critical mineral supply chains. Australia's Lynas Corporation is already expanding its processing capacity with support from the US. serving as a critical alternative. Beyond government deals, innovative companies like Luca Resources in Australia are fighting this market structure itself. They're moving away from pricing linked to the volatile China controlled Asian market index and instead developing bilateral contracts with customers featuring floor and ceiling prices. This provides a long term price certainty that Western investors need to commit the massive capital required to build independent supply chains, offering a pathway to a genuinely sustainable non Chinese rare earth industry. The rapid expansion of AI is creating a complex new dependency, a trilemma between AI, energy, and minerals. First, AI's energy appetite is staggering. Total electricity consumption of AI data centers, AI and cryptocurrency would more than double to over 1000 terawatt hour by 2030. So 1 terawatt hour equals 1 billion kilowatt hours. Now, in the US, data center consumption alone is projected to rise to nearly 9% of total electricity use. This means AI is no longer just an energy optimizer. It's a new structural driver of global electricity demand. Second, consider the material energy debt. Manufacturing specialized chips, especially advanced 3 nanometer wafers used for cutting edge AI, consumes approximately 2.3 megawatt hour of electricity per wafer. Third, mineral consumption is concentrated. By 2030, data centers could account for a stunning 11% of global gallium use and 3% of rare earth consumption. This intense demand forces AI infrastructure to cluster only in jurisdictions with low cost, stable, and reliable electricity, reinforcing existing economic asymmetries and strategic control in a handful of actors. The nexus of energy and materials highlights a critical challenge for the global south, particularly Africa. The continent is indispensable to the material foundation of the AI economy, holding significant reserves of minerals like cobalt, manganese, and rare earths. The DRC, for instance, provides over 70% of global cobalt. But Africa faces a severe infrastructure constraint. Over 600 million Africans lack reliable electricity access. Grid reliability is inadequate for the demanding needs of AI enabled systems. The risk is a structural dependency, often termed digital recolonization. Africa risks being locked into the historical role of supplying raw materials, which is extraction, while simultaneously remaining dependent on foreign actors for high value compute and cloud services, which is processing and design. To achieve sovereign participation in the AI economy, the strategic priority must be to translate mineral endowments into integrated industrial capacity, moving beyond raw resource supply to regional processing, manufacturing, and data infrastructure development. Our pursuit of technological supremacy relies on a linear extractive model that carries devastating environmental and social costs, often creating what we call sacrifice zones. The processing of rare earths is chemically intensive and environmentally destructive. Producing just 1 ton of rare earths can generate up to 2,000 tons of toxic waste, often containing carcinogenic, meaning cancer causing, heavy metals and radioactive elements like thorium. The result is environmental damage, like the vast toxic tailings lakes seen in places like Boto in China. This also raises severe ethical concerns. The heavy rare earth essential for EVs and defense magnets are often sourced from places like Myanmar, linked to ionic clay deposits. There is next to no transparency around the environmental, social, and governance practices in those regions. This forces global EV manufacturers to indirectly sponsor environmental degradation in their pursuit for essential materials, creating a profound conflict between climate goals and supply chain realities. The environmental impact transitions directly into a severe global public health issue. The long term, large scale mining and utilization of rare earths lead to chronic human exposure. These elements enter the body through multiple pathways: inhalation of atmospheric particulate matter, ingestion through the food chain, and even iatrogenic exposure from medical contrast agents containing elements like gadolinium. Once inside, REEs accumulate in various tissues and organs, leading to severe multisystem dysfunctions. For the respiratory system, exposure is linked to pneumoconiosis, pulmonary fibrosis, and even lung cancer. In the nervous system, these can cause blood-brain barrier, causing brain damage, memory impairment, and neurodegeneration. Furthermore, long-term exposure can lead to adverse reproductive outcomes, including fetal loss and reduced sperm quality, proving that the costs of the AI race are being borne by human health and fragile ecosystems across the globe. So, where do we go from here? Now, we stand at a crossroad defined by the geopolitical competition for these materials. We face a fundamental choice. Do we compete for control over a finite, environmentally damaging, and politically fraught resource, or do we collaborate to fundamentally redesign the technology system itself? The strategic path forward, like distributed weave, lies in technological sovereignty. This means massive investments in material science innovation to develop a viable alternatives to rare earth dependent technologies like iron nitride magnets, decoupling key sectors from geopolitical risk. It also demands treating waste as a resource. We must turn the vast amounts of discarded electronics in the urban mine into a strategic domestic reserve by investing in advanced recycling technologies to shift power from geopolitical or geological control to intellectual leadership and technological innovation. True resource security is achieved when we create resilience through dematerialization and distributed capacity, ensuring that the benefits of AI are not achieved at the cost of global stability, environmental health, or human lives. With that, we come to the end of the show. If you like this video, please consider supporting our work. All you have to do is click on join right below this video or go to the description of this video, and at the very end, you'll see the link for joining us as a member. In any case, we sincerely hope that you like, subscribe, and share this video. Thank you so much for watching the AI with Arun Show.